So let's try to do our coffee drinking puzzle. So actually, rather than starting with 11 of us trying to get 11 drinks out of 6 possible choices, let's first look at a little bit more manageable size puzzle. Say there are 2 students, and rather than going to Jumping Bean, they decided to go to Treats, which has 4 kinds of coffee. Medium, let's say medium house, decaf, and flavored. So how many different combinations can 2 students get if they have 4 choices and each gets 1 drink? So your first reaction may be, okay, I know the rule of product, so let's use it. There are 4 choices for the first person, 4 choices for the second person. That must be 16 possible orders. But in this case, decaf and medium would be the same kind of order as medium and decaf, and we would count it twice. On the other hand, medium and medium we would only count once, so dividing by 2 is not really going to give us the right answer. So what is the right answer? Let's do it by actually listing all the possible variants, and let's list them in alphabetical order. And moreover, we are going to list only one string for each possibility. For example, we are just going to mention decaf and medium, and we are not going to mention medium and decaf because it's the same order. So here are the possibilities. They both can get decaf. They can get decaf and flavor, decaf and house, decaf and medium. That's 4. So now, if they don't get decaf, they can both get flavored, one flavored, one house, and one flavored, one medium. If they're not getting decaf or flavored, they can get 2 house coffees, house and medium, or 2 mediums. And this gives us 10 combination of drinks, which is a little less than the 16. So in this particular case, you might be able to calculate it by, say, subtracting the 4 possibilities with the same, dividing by 2, and adding the 4 back in. But as soon as you get 11 people, that becomes unwieldy, because you need to know how many common choices are in each category, and that's just too much to count. So let's count them in a slightly different way. So rather than using those 10 string, decaf, decaf, decaf flavor, decaf house, decaf medium, and so on and so forth, let's encode the order like this. I'm only going to use 2 symbols, C for coffee, any of the 4 kinds of coffee, and also vertical line for divider. So what is the divider, what I'm talking about? Well, the way I'm going to specify the order right now is to say I have 4 categories, and I put a line, a divider between items in first and second category, another divider between second and third, another divider between third and fourth. And what are the objects between which I'm putting the dividers? That's our coffees. So note that here, if we have k categories, we need k minus 1 dividers. If you need to put separator between k things, you only need k minus 1 separator, because 2 things on ends, they don't need the outer wall, you know which one is where. So here's an example. For example, if I'm writing a string C, divider, divider, C, divider, that means 1 coffee of the first type, well, let's say decaf, no coffees of the second type, 1 coffee of the third type, and no coffees of the last type. Or instead, if I write divider, coffee, coffee, divider, divider, that will mean 2 flavored coffee. Hopefully you kind of see how you could encode orders in this way, kind of without ambiguity. All you're doing is you're saying everything that comes before the first divider encodes my decaf, between first and second is flavored, between second and third that's house coffees, and what's after the last divider is mediums. So now with this notation, we could finally count how many orders those two students can make if they have 4 choices of coffee. And the reason is that now we have a string consisting of 2 types of symbols. Some of them are C's and some of them are dividers. And there are 5 places in the string, and 2 of them are going to be taken by the letter C and the rest are going to be taken by dividers. Or you could say 3 of them are going to be taken by dividers and the rest are going to be taken as by coffees. All we need to do now is to say how many ways there are to select 2 places in a string of length 5. But wait a moment, we already know how to do this, because it's just choosing 2 options out of 5. That's our combination formula, and choose k. So in this case, we have 5 possible places, 3 plus 2 is equal to 5, and we are choosing two of them to put the coffee symbol. It's 5 factorial divided by 2 factorial times 3 factorial, and we get 10. So when 2 students want to get coffee at treats, they have a choice of 4 kinds of coffee. They can place 10 different orders, and that's exactly the number that we got when we listed all the possible combinations. So how to generalize it? Let's go back to our initial puzzle with 11 people and 6 types of drinks. And in general, you could just have n people and some kind of k number of drinks. So now the formula becomes, we have the number of choices of whatever the number of people is out of number of people plus number of dividers. So if we have 6 types of drinks, there are 5 dividers, we have 11 people, so that gives us 6 strings of length 16 consisting of 11 symbols for C and 5 dividers. How many ways to put those 11 symbols, or equivalently those 5 symbols, in a string of length 16? It's 16 choose 11, same as 16 choose 5, and we get 4,368 possible orders that 11 people can place when they have 6 choices. So in general, the number of ways to select are objects. So here I'm slightly changing notation. I'm selecting R objects out of n categories is R plus n minus 1, choose R. So here R is 11 and n is 6. So just to sum up, we looked at several ways of counting things, several ways of selecting k out of n objects. If we just look at strings where every symbol is allowed to be one of n objects and there are k symbols, then we get n to the k possible strings. So this is like our pin number example. If order still matters, but we don't allow repetitions, it's our R permutations. So this is like selecting first, second, third place in a contest. If we allow repetition but don't care about the order, we have this objects and dividers example, combinations with repetitions, where the formula is number of, let's say, people making an order plus number of categories they can choose from minus 1. Choose the number of people making the order. And finally, if we don't care about order and we don't care about repetitions, we get n choose k, which is n factorial, divided by k factorial times n minus k factorial. So here's the puzzle for next time. Americans like to do this puzzle with the word Mississippi, but in Canada, let's pick something a little bit more Canadian. There is a town in BC called Osayus, spelled with 4 O's and 2 S's and a Y. And now imagine that you're playing a game of Scrabble and you have 7 pieces in front of you, and you realize that they make the word Osayus and you put it on the board. So how many different ways could you have the letter of the word Osayus on a rug in front of you before you actually made the word out of them and put them on the board, if the O's are indistinguishable and S's are indistinguishable? So OOSS OOY is one possibility, and doesn't matter if it's the first O of Osayus, that's the first or the second O of Osayus, you cannot tell them apart. And by the way, here, when you put letters on the rug, they absolutely don't have to form a word. You could put them in any possible order. So for next time, think how many different ways can you place the letter of the word Osayus on the rug if you cannot distinguish the O's and you cannot distinguish the S's.